Okay, so finally we can start thinking about the complex roots case, which is my favorite case. It's really where the most interesting stuff happens. And in this case, what we have, if I can find my pen, found it. What we have is lambda equals alpha plus I beta, maybe for lambda 1, and then lambda 2 is alpha minus I beta, where I is the so-called imaginary unit, sometimes described as a square root of -1. And when we do this, so we will still have, as a perfectly valid general solution, x of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t. That is a perfectly valid general solution, except for the fact that it is complex valued. So if lambda 1 is alpha plus I beta, then e to the lambda 1t is a complex valued function rather than real valued. We were after real solutions. When we say we want a general solution, we want a real general solution. We want it to allow us to make predictions about actual systems that we may have described using real valued functions. For example, the spring mass system. A damped spring mass system looked like this, had this kind of differential equation, right? And x of t represented a physical quantity, the displacement of the mass from an equilibrium position. Or the RLC circuit with no power source also had this kind of differential equation, and the unknown function x of t was what we called q of t, was the charge on the capacitor plates. Imaginary values or complex values don't necessarily mean anything. We want real values, right? Because they measure actual quantities. We want one number out rather than two numbers. And a complex valued function really is kind of like a function that gives you two numbers out, because it's giving you a real part and an imaginary part. So let's get into a discussion about complex numbers. We're going to have to. Okay, so here's what we have to do. We have to learn how to interpret what is e to a complex number times t. So we need to be able to interpret e to a complex number, and we need to understand it well enough to be able to do calculus with it, so we can take derivatives and things like that, and use the chain rule and stuff. So that's one thing that we need: understand e to a complex number and understand it well enough to do calculus stuff with it. And the second thing we need is figure out how to turn this complex solution into a real solution, which is ultimately what we want, is a real solution. Okay. So let's just introduce complex numbers. Without the context of exponentiation or functions, let's just introduce complex numbers in general. And I'm going to say that this video also is optional if you're familiar with complex numbers. So at this point, you can skip to the next video if you're already familiar with algebra for complex numbers. And in the next video, I'll just get into the exponential parts of things. But here it'll just be algebra. Okay, so what is a complex number? You can think of it as a pair of real numbers. So if a and b are real numbers, then a complex number is just the two real numbers paired up together. And we literally think about it as a point in R2 in the plane. So go over a units, go up b units, and then you would call the point a comma b. Except we write it differently. Instead of writing it as ordered pair a comma b, we're going to write it as a plus b times I. So think of this as just the way that we write ordered pair a comma b. Why write it this way? Well, because we're going to allow ourselves to add and even multiply complex numbers, so pairs of real numbers, in such a way that I, which is 0 plus 1i, so I sits right there, 0 over and 1 up in the complex plane, we're going to arrange things so that I squares to be -1. So in other words, we're going to arrange things so that if you take 0 plus 1i, if you take that pair 0, 1, and you square it, then you get -1 plus 0i, which is also called -1. So this is written I for short, and this would be written -1 for short. So -1 is here, -1, 0. So we're going to arrange things so that this point in the plane squares to be this point. So this is what people mean when they say I stands for a square root of -1. It's not, yeah, I say a square root of -1 because when you do this in the end, you end up with 2 square roots of -1. Both of these end up being square roots of -1. Okay. So what I've said so far is that complex numbers are pairs of real numbers written in this funny way because when you take this pair, it's going to end up squaring to give you this pair. So 0, 1 squares to -1, 0. But what does that even mean, squaring? It means multiplied by itself. But what does that even mean, multiplying a pair of real numbers by another pair of real numbers? So I need to describe to you how multiplication is going to work. Like if I take a plus bi, which is some dot somewhere in R2 in the plane, and c plus di, then that's going to be some dot somewhere in R2, cd. How do you multiply these two dots together? Excuse me. So to multiply the two dots together, I'm going to give you some complicated long rule for multiplication. Except I will not give it to you that way. Instead, a simpler way to describe it is use the notation a plus bi, c plus di, and do what it looks like would be the right thing to do. FOIL. So just distribute. So what would you get? AB, or AC, right, plus ADI. Not sure why I put this parenthesis here. AC plus ADI plus BCI plus BDI squared. So in other words, AC plus AD plus BC all times I plus BDI squared. And then I want you to only use the rule I squared equals -1. That's the only rule you need, and that will tell you exactly how to multiply any two dots in the plane. So if you use the rule I squared equals -1, then this becomes -BD. So this is the rule that you need to remember, and that's it. So then I'm going to move the BD over to here, so I see AC minus BD plus AD plus BC I. Okay, so you see we have multiplied two complex numbers, so these are two dots in the plane, and after multiplying them we got a new complex number. This is the first coordinate and this is the second coordinate. So it sits AC minus BD over along the x-axis and then AD plus BC up or down along the y-axis. Okay, so much for multiplication. What about addition? So if I take a plus bi plus c plus di, then what's that? Do what it looks like. Again, this is much easier than multiplication. So just add the components, the first component and the second component. So these, like what I'm drawing as horizontal versus vertical component, or first versus second component, these are called the real and the imaginary parts of a complex number. So when you see a complex number like a plus bi, then this is called the real part, and this is called the imaginary part. Now, notice that both are real numbers. The real part of a complex number is a real number, and the imaginary part of complex number is also a real number. So these are both real numbers. The imaginary part is just called the imaginary part because it's the second component, and it's the part that's multiplied by I. Okay, yeah, so what about visualizing these operations? So when you're adding complex numbers, that's pretty easy to visualize because it's just like vector addition. So let's say you have, here's the plane, let's say this is A, B, and this is C, D. Then think of them as vectors coming out of the origin, like this. And then A plus BI, which is what this dot represents, and C plus DI, which is what this dot represents, when you add them, you get A plus C, B plus D. So that's the same as what you get when you add vectors. You can use this kind of parallelogram law. So here, let me describe this better. What I'm doing is taking this blue vector here and just putting its tail at the head of the first vector. And there is A plus C, B plus D. So when you add complex numbers, it's just vector addition in the plane. When you multiply them, it's something that looks a lot more funky and weird. And if you want to visualize what's going on with multiplying complex numbers, then really you want to use polar coordinates to describe what's happening. But let me get to that later if needed. I might actually just leave it out of this course since it's not super crucial that we visualize everything we do. Okay. Yeah, I think that's all I need to say about adding and multiplying. What about dividing? Okay, so this is one of the amazing things about complex numbers, is that you can divide. So let's say I have A plus BI divided by C plus DI. What does that mean? So when I say you can divide, I mean you can divide two complex numbers and end up with a complex number. So somehow if I take this thing, which represents a dot in the plane, and divide by this thing, which represents a dot in the plane, then I get another dot in the plane. Well, what this is supposed to mean, the division, is it's supposed to represent that complex number, that dot in the plane, which when multiplied by C plus DI gives you A plus BI. That's what it is. But how do we compute it? How do we compute what its real and imaginary parts are? So basically, where is this dot in the plane? What is its location? How far over and how far up? So there's a trick for computing it, which is multiply by what's called the complex conjugate. So if you have a complex number, A plus BI, then the complex conjugate, which we denote by putting a bar above it, is A minus BI. The complex conjugate is the complex number you obtain by taking the imaginary part and flipping the sign, so adding a negative, tacking on a negative. So the trick for computing what is this division is multiply the numerator and denominator by the complex conjugate of the denominator, like so. And why does this trick work? This trick works because in the denominator you end up multiplying a complex number by its own complex conjugate. And when you do that, you get a real number. So see if you can work this out and convince yourself. C plus DI times C minus DI ends up being C squared plus D squared. If you just do the algebra, FOIL it out, distribute, you actually get this. You might think you'd get something plus I times some other thing, but no, you just get this plus I times 0. So that's why it works. And then in the numerator you get, I guess, AC plus BD, because it's B times negative D times I squared, and then plus something times I, and the something has the cross terms, so BC minus AD. Okay, so do you see how this is a complex number? It's AC plus BD over C squared plus D squared plus I times BC minus AD over C squared plus D squared. This is a pair of real numbers. So overall, what we were doing was we were computing A plus BI over C plus DI, right? So apparently if you take this dot in the plane and divide by this dot in the plane, then you get this dot, which is this far over and this far up. So by the way, there's some notation for what I'm describing here, real part and imaginary part. So if you have a complex number like z, we often use the variable z, we write re, capital R, lowercase e, z, to represent the real part of z. And we write im, capital I, lowercase m, z, to represent the imaginary part. So again, they are both real in the end. So if you do re a plus bi, then that's a. If you do im a plus bi, then that's b. It's not bi, it's b. So they are both real. They're just picking out the components. Think of re as saying, how far over is this point? And im as saying, how far up is this point? And they can be negative, which means you're over to the left or down, actually. For example, what we are seeing here, what we are observing here, is that if you want to know the imaginary part of this complex number, this quotient, then the imaginary part is this real number, BC minus AD over C squared plus D squared. Who knew? The imaginary part of this is that. That would have been hard to know if you didn't know about the trick of multiplying by the conjugate. So this trick is not just like a random trick. This is crucial for basically doing anything with complex numbers, is being aware that you can do this in fractions to write them as real part plus imaginary part. Sorry, not real part plus imaginary part. Real part plus imaginary part times I, since it's this which is the imaginary part and not this.